Okay, so my talk is going to be about the Hopf category of Frobenius algebra. So I'm gonna dive right in, and we're gonna talk about the navigation plan for today. So I want to first start with a case for multi-object structures. So the Hopf category in the title is a generalization of Hopf algebras, and it's a multi-object structure. So I want to talk first why they're useful and why we consider them at all. And the main motivation for our research was topological quantum field theories. So I want to also take a few words about that. And then this is the core chapter. Probably we talk about measurings and co-measurings of Frobenius algebras. And I want to conclude with some examples that I calculated and an outlook on how could this research go further. So starting with someone hopefully everyone knows, I wanted to look at just the definition of a group. So this is something that's quite familiar to everyone. We have a set and a binary operation, and for this operation we have two specific things: a neutral element and an inverse. I kind of suppressed here that we also want associativity. But particularly for the rules concerning the neutral element or the inverse, we have these two formulas. And I kind of wrote them like this because we want to look at groups in a different lighting, and the way we do that is by generalizing these formulas here. So examples for groups, there are plenty, and I think probably everyone has their favorite group. But I also wanted to mention fundamental groups of topological spaces or manifolds, if that is something you're interested in. Or for example, Lie groups, where we put even more structure on the set. So, and another way to look at groups that is particularly interesting for me as a category theorist is we can define a group as a category. And the way we do that is we define it as a category with one object. And the way at looking at the group is by just considering the morphisms between this one object. I call it here a point. And for every group element, we consider a morphism from the point to the point. The way of doing that is nice because implicitly the associativity is already given in the definition of a category. So if we have a category and we want to compose arrows in a category, then we already want an associativity. And also for all objects, we have an identity. And particularly here in that case, where we all just have one object, there's one identity morphism from the point to the point. And a group is a specific category where we want that every morphism is invertible. So we have a map S that maps some morphism to its inverse. So the unity condition translates to the first formula here, and the invertibility condition translates to the second formula here. And when I write a big G, I mean the identity that just leaves the elements untouched. So in the second case, I apply G, I leave G as it is in the first component, and on the second component, I apply my antipode, my map S, and afterwards I multiply them, and I should get the identity morphism as we expected. And a benefit of the way of looking at categories like that, it's way easier to generalize them. So if I want to put more structure on G, I just can talk about enriched categories, and that formalism is already there, and we can use that to talk about the groups in enriched groups, or I don't know, but topological spaces or manifolds or whatsoever. But another way, this is the way I wanted to go is here we just have one object. What happens if we allow other objects? So this is the definition of a groupoid. If we have a category with not necessarily one object, but multiple objects, and every morphism in that category is invertible, we speak of a groupoid. So particularly for every point in my category, I have morphism spaces here denoted by the GXY. And for every 3 points, I have a multiplication that can connect an arrow from x to y with an arrow from y to z, and the result is going to be an arrow from x to z. And particularly here we have multiple identity morphisms, which are maps from x to x. And I have a map that goes from, that reverses an arrow, and these maps some arrow from x to y to its inverse. And particularly here we have the same formula as before, but we have to make sure that we use the right multiplication, here denoted by the indexing x, y, y, or if we use the right identities. So it's basically the same thing, but we have to be more careful because we always have to consider where does an arrow start, where does it end. And the examples for that are just collection of groups. I can take some groups and I put them together, and I kind of artificially put them together by adding the empty set between points that are different, and between the same points I can just add a group and consider it as a like in the case before of just morphisms from one point to one point. And since I mentioned fundamental groups in the group example, here I want to mention fundamental groupoids, where we have more things to consider. So we also consider just paths from x to y and not just loops starting by x and ending by x. So yes. So this is already one example of a multi-object generalization. And then another way you can go with the definition of a group, which is also something that is widely known, is we can consider Hopf algebra, which is like a cousin of a group. So in a Hopf algebra, we consider an enrichment also, and this enrichment is over some monoid category. So if we go back to the slide of the groups, in the second line, we have always a couple of G, and it already smells like we want to use a co-multiplication here, and this is exactly what we do. So a Hopf algebra we consider to be a category enriched in comonoids over some braided category, and it's particularly we have an antipode satisfying the antipode condition. So specifically for and in the specific case of having a Hopf algebra, we only consider one object. So everything starts from the same object and lands in the same object. So a Hopf algebra can be considered as the homomorphism space from one point to one point. This forms a groupoid. This forms a comonoid, and particularly the composition of arrows should be a coalgebra map or comonoid map, and the unit should be a comonoid map. So here are the formulas, just who correspond to the cases before. But note that we don't consider just a tuple of two G's anymore, but we use our co-multiplication. So this is a way of seeing that the groups and the Hopf algebras are quite related. So Hopf algebras have a wide variety of applications, and I just put some examples here. Group algebras. So for a field and a group, you can always consider the group algebra, and there's a natural way of endowing that with the structure of a Hopf algebra. And another really interesting and important example is an enveloping of a Philly algebra. So the way of looking at a Hopf algebra in that way, again, with having a category with one object and being enriched over a comonoid, makes it much easier to justify why we can generalize it by just allowing more objects. And this is exactly what a Hopf category is. So this is the main definition I wanted to come to. So for a braided monoidal category, a Hopf category is just a category that is enriched in comonoids, and we have an antipode map. So particularly for 2 points, we can consider the Hom spaces, and these should be comonoids with so for every 2 points I have a specific co-multiplication, a specific co-unit, and the multiplication, the composition of arrows should be a map in the category of comonoids. And the same holds for the antipode, but here we have to reverse the multiplication just by the way we compose arrows. So these formulas that are here are much less scary if we see how they came to be. So they're the same formulas we used for Hopf algebras, but just also considering where does an arrow start and where does it end. So again, examples, we can just consider collections of Hopf algebras and artificially put them together by putting the zero vector space in between them if we were working over vector spaces. And a particular case is if we work over Z. So if we consider Hopf categories over Z, this is just Groupoids. So we can go back to the original idea. And the specific Hopf category I want to talk about today is the Hopf category of Frobenius algebras. And the next few slides will motivate how we get to there and how we can show that we can find some Hopf category involving Frobenius algebras. So I want to end my case for multi-object structures here. I hope I convinced you that it is something we want to look at. And I want to completely jump the topic now, and I want to start explaining what a TQFT is. And one of the components using TQFTs is coalgebras. So I want to define a category of coalgebras, and I do that step by step to see what's going on. So the objects in my category of coalgebras are just closed-oriented n-1 manifold. So for every n natural number, I can build a n-dimensional coalgebras. And the objects here are just dimensionless and closed manifolds. So if I have, for example, in this picture, this is the two-dimensional case. I have one-dimensional closed-oriented manifolds, which are just collection of circles. When I have some objects, I want to consider morphisms, and morphisms between such closed manifolds are now just manifolds with boundaries, such that the boundaries are the objects which describe the morphism. So for two objects, which are in that case collection of circles, I consider a manifold that has the upper boundary and the lower boundary, and the way I can encode that is by orientation. I don't want to put too much details on because talking or like specifying what kind of manifolds, there's a lot to say, but it's just a general idea on how to build these categories. So how do if I have objects now, I have morphisms, how do I compose morphisms? And this is by gluing them together. So in the picture here, I have the morphisms from 3 circles to 2 circles, and I can glue it together with some map coming from 2 circles to the empty manifold, which we also consider. And the way we glue them together, we can see that this is a series composition map for this category. So if I say composition, I also need to clarify what are the unit objects, the unit morphisms, and in that case, we just have cylinders. And a specific way I can also, something particularly I can also endow on this categories, I can endow a monoidal structure here by just building disjoint union of objects, disjoint union of morphisms. And the monoidal unit in this particular case would be this empty manifold that we sometimes also endow when indexed to see what kind of manifold we consider it to be. And the last thing we also see here is that this monoidal structure is naturally symmetric. So we can just switch around the disjoint union and see that we have a Fourier symmetric structure on it. So this altogether is the category of coalgebras, of n coalgebras, and it forms a symmetric monoidal category. And now it's from this description, it's quite easy to define a TQFT. I just want a second symmetric monoidal category. This can be vector spaces, this can be modules, or yeah, be creative, whatever interesting symmetric monoidal category you find. you can define an n TQFT to be a monoidal, symmetric monoidal functor from the cobordisms to this category V. And we specifically call this category V the target category. So the classic definitions would be real vector spaces or vector spaces over a field. But by considering in such a wide categorical description, we can be much more free in considering more. So I talked a lot about that. Maybe let's get some examples. Let's start with the easiest one. If I start with one-dimensional TQFTs, my cobordism category is just zero-dimensional manifolds, which are points, and I have an orientation on these points, so plus or minus, and I can always, for some collection of points, I can consider some one-dimensional manifolds between them, cobordisms, which in that case are lines. And the way they connect are, I can go from a plus to a plus, but then I have to go to the out boundary, or I can always eliminate a plus and a minus from the same. But it also can happen that I just have an open close, so I create 2 points and I close these 2 points like this circle imitated in the middle. So this is a quite straightforward, easy description of the cobordisms, and if I look at the category of vector spaces, it's quite easy to see that I can classify all my TQFTs by vector spaces. I just need to choose a vector space for so if I map a point with positive orientation to this vector space, then by making sure that the TQFT satisfies all conditions, the minus point needs to be mapped to its dual, and by having a dual, we know that the space must be finite dimensional. And yes, so this is the easiest case. So completely have a complete classification for the one-dimensional case. So this is the first theorem. If we choose a V as a vector spaces over a field K, then all one-dimensional TQFTs are classified by finite dimensional vector spaces. We also have a classification for two-dimensional TQFTs, which are commutative Frobenius algebras. And here, because the cobordisms in two dimensions are quite simple, we know that all the objects are just generated by a collection of circles. We only need to know what does the TQFT do on a circle. And particularly here, evaluating the set on the circle, we get some finite dimensional vector space, and all the conditions imposed on the TQFTs make sure that it forms a Frobenius algebra. I want to talk more about Frobenius algebras later, so maybe just mention how this story goes on in the classification of TQFTs. So for three dimension, we don't really have a complete classification, but we know that if I have a Hopf algebra, there's a way of creating a three-dimensional TQFT. And I have to impose more conditions on the Hopf algebra, and particularly here it's quasi-triangular. But there's a wide variety of research there, which I don't want to get into details. So the nice thing about the two-dimensional case is we can draw it, and I have a beautiful sketch here. So everything I need to consider by looking at two-dimensional TQFTs are these generators. So I have identities, I have a co-unit, I have a unit, I have a multiplication, a co-multiplication, and a switch map. So for example, if we take the third sketch here, it's something that starts with two objects and maps to one object. And if I map this circle to the same vector space, I get a multiplication from A, tensor A to A. And by looking at all these relations that need to be satisfied, we can conclude that the multiplication needs to be associative, there's a unit, and it needs to be commutative. And dually, for the co-multiplication, we have the dual actions. So already we know that if with Frobenius algebras have to satisfy these conditions, and particularly how do these two structures behave together, there's the Frobenius relation. So in the thing I particularly like about this subject is you can see the geometry, and you can define the algebra, and you can see exactly what's going on. So how do I define a Frobenius algebra? I define it by just using these conditions. So in particular, Frobenius algebra, I have a 5-tuple of a vector space. I have an algebra structure in it with multiplication mu in a unit. And I have a coalgebra structure in it that is co-associative and co-unital. And I particularly want this Frobenius condition. And so this is the way it looks like in an algebraic diagram, but it basically is the same than with the sketch we saw. So this is a Frobenius algebra in general. If we impose commutativity or co-commutativity conditions on it, we speak of a commutative Frobenius algebra. And what is a classical morphism between Frobenius algebra is a map that conserves both structures, the algebraic and the coalgebraic structure. So we want a map that is as well an algebra morphism as a coalgebra morphism. So now we kind of have a basic understanding of the lower dimensional cases, and by playing around with that, you can arrive to some observations. And one of the motivating observations we had in the beginning was, if we look at a 2-dimensional cobordism, which looks like this, for example, and we just cut it through, we do a cross section through a plane, then what we get has the similar shape of a 1 cobordism. So this was our naive observation, I say, because we quickly realized that with the switch map, we don't really have a way of cross-sectioning it. But just by looking at that, we can make a speculation that if we find some morphisms, some functor from the 2-dimensional cobordism category to the 1-dimensional cobordism category, we can, and we use a 1-dimensional TQFT-Z, we can, by composition of these two functors, create a 2-dimensional TQFT. So it would be really nice to have such a functor, but as said, it's not that easy. But there's a framework which I found where this all makes sense. That is by Lauda and Pfeiffer, and they also consider wider classes of cobordisms. But yeah, it was our starting place, but the algebra that came from our motivation is still valid. And the way we started was we know that the cobordisms in 2 dimensions are generated by circles in the object case. And our cross section maps the circles to a positive oriented point and a negative oriented point. And a TQFT then maps that to the dual of a vector space tensor product, the vector space itself. And by a well-known equivalence, this is just an endomorphism space on V. And it's kind of fascinating that it also fits the description of Frobenius algebras, because if I look at a finite dimensional vector space and I look at all the endomorphisms, so matrices between the same vector space, then this forms a Frobenius algebra. This is a non-commutative Frobenius algebra, so it doesn't really fit the description I was telling earlier, but in this newer sense of open-closed, wider cobordisms, this can be still considered. So by this lower dimensional observation, we were speculating if something like that also happens in higher dimensions. So if I just go 1 dimension higher and I look at the 3-dimensional cobordisms, 2-dimensional cobordisms, is there a way of cross-cutting a cobordism so that I can generate 3-dimensional TQFTs just by looking at 2-dimensional TQFTs that I already classified? So we don't really know what's in this diagram. How should I cross-section something, or what is but if we just look at the endomorphism space of a Frobenius algebra, is there a way of endowing that with a Hopf algebra so we have a more evidence that there could be a connection between them? So this is where my title led to. We wanted to have a Hopf algebra structure on an endomorphism space, and in the wider consequences, if I consider all Frobenius algebras, also different ones, can I know a Hopf category in it? So there's a classical way of looking at Frobenius algebras that I already mentioned. If you look at the morphisms to be Frobenius algebras, and we look at Frobenius algebra morphisms, we can build the classical, I call the classical category of Frobenius algebras. So all my homomorphisms between A and B are maps from A to B that preserve my co-multiplication, my multiplication, my co-unit, and my unit. And again, we have something that looks like an F tensor F. So if we remember in the group case, I had a G point G. So this is already quite suspicious that maybe we can work with a second co-multiplication here. And the reason why we probably don't want to work with that categories is this theorem that is widely known. If I look at Frobenius algebra morphisms, I can always invert them. So I can always find an inverse to them. And speaking in the terms I defined earlier, the category of Frobenius algebra with Frobenius algebra morphisms is a groupoid. So every morphism is invertible. And I don't want to really bore you with the proof, but just give you some overview on how one proves that. The key element here is the Casimir element, which is just if I apply the co-multiplication on my unit, I get some in Sweedler notation, some element E1 and tensor E2. And if I have a morphism of Frobenius algebra, then it preserves these Casimir elements. And the Casimir elements have the nice property that by the Frobenius condition, if I multiply with something, I can always multiply it on the other component. So I can kind of jump out of some calculations. So the way of showing that every Frobenius algebra morphism is invertible is by constructing an explicit inverse. So in that case, this is the formula how I do it. You just apply the h to the second part of the Casimir element, multiply by b, then use my co-unit to get a number and multiply it with the first component of my Casimir element. And that works out. And here's the calculations that you can check. By applying first g and then h, or first h and then g, we make sure that we still have an identity, right? Just using the properties of the Frobenius algebra. So the way I presented this proof is we want to generalize this proof in a wider setting. And what wider setting are we using? We want to find a bigger Hom space to consider. We want this Hom space to have a coalgebra structure. So particularly the way of looking at that is if I have a coalgebra and I have two vector spaces and I have a map that goes from P tensor A to B by the Hom tensor relation, I can consider that just to be a map from P to the homomorphisms from A to B. So a way of, instead of looking at just homomorphisms from A to B and specific relations, I want to look at subspaces of my homomorphisms, and particularly I want to have a coalgebra structure in it. And I use this notation often to make sure that these coalgebras P I consider can be interpreted as parts of the homomorphism space. So we are on the search for a bigger Hom space to consider between Frobenius algebras, and one thing that was really fruitful is looking at measuring. So the definition I put here doesn't really specify what A and B R in general, but this works for wide classes of structures on vector spaces. So if you consider this this paper I mentioned here, you can see that this works for omega algebras in general. So there's a lot of ways of looking on measurings, and a lot of the theorems I mentioned later. Okay, I think my laptop just had a breakdown. Can you hear me still?
Yes. Yes.
Should be back up in quite a second, I hope.
We can start again soon.
Okay. Okay. Am I back on?
Yes.
Okay, sorry for that. My laptop decided to just shut down. Okay, so the last thing I was talking. Oh, so for all the theorems I use later, there's a more wider structure to consider them. So what is a measuring between two algebras? In that case, I start with a coalgebra, and I have the specific map phi that maps. This map phi starts with p tensor A and maps into B, and I put specific conditions on it, which are here. And I don't want to like walk through the whole thing, but the key element is here that if I look at the last line here, if I apply P on a product in A, I don't just, in the case of an algebra morphism, I would have PA times PA bar. But since I don't want to have an algebra morphism, I want a wider structure here. I first co-multiply my element P, and then I apply it to A. And the same is for the unit. I just don't want to conserve the unit by I conserve the unit up to some multiplication of the co-unit. There's a wider class of things I can consider, and I use this coalgebra structure here particularly to have a wider class of morphisms. So this is a measuring of an algebra, but it's not the full picture of how to measure from one Frobenius algebra to the next. So I also need to consider the coalgebra structure. And it turns out in that case, if I use the proper way of defining this, it's just a coalgebra morphism. So I only need to loosen the algebra condition a bit and put these two conditions together to have a measuring of Frobenius algebras is a measuring of an algebra and a coalgebra morphisms at the same time. And the reason, for example, why I look at that, because this is a small note here. What happens if I apply P to the Casimir element? So here I cannot just apply 2 times P on an element, but I first co-multiply my P, and I apply it to my Casimir element E. So it's the Casimir element in B up to, again, multiplication by some co-unit, by the co-unit of P. So this is just the definition of one measuring, but I want to specify which measuring do I use. And luckily, there's a theorem that there's a universal one. So there exists this a specific measuring from some structure A to a structure B. This holds in different ways, But specifically in our case, if I have two Frobenius algebras A and B, then there exists a universal coalgebra that, if I have any other co-measuring, this factors through my universal measuring. Specifically, if I look at A and B to be the same, then the conditions imposed here are equivalent to saying that I have a universal action. So if A and B are the same, I can speak about universal acting coalgebra. So yeah, this is a really, really strong, powerful theorem, and we use it by just defining a new category, which I call the non-classical category for Frobenius algebra. And instead of using all Frobenius algebra morphisms, I consider my Hopf space to be this universal measuring coalgebra. So in this new category, this new non-classical category for Frobenius algebra, this forms a Hopf category. So this is the main result we found, and this is the thing we worked on. And the way to prove this new theorem is by just adapting the proof accordingly to the classical case where we prove that every morphism of Frobenius algebra is invertible. So I'm not going through the whole proof, but the key fact here is I define a new measuring, and the way this measuring works is by basically using the same formula. Then in the case of Frobenius algebras, I first consider the Casimir elements. I apply my P on the second component, multiply by B, use the co-unit, and then multiply that in A by the first component. And if I define my measuring like that, I can show, okay, this really forms a measuring, and by the universality of my universal co-measuring, universal measuring, I know that I can find a map that specifically does what I want on my coalgebras, on my measuring coalgebras, such that I have an antipode. So this is just a nice way of adapting that using a similar proof, and it quite holds. So if I think I still have some time, so we can also talk about the dual side. I can do this whole program I just did by looking at measurings. I can also dualize everything, and then I can look at co-measurings that instead of looking at maps from P tensor A to B, I can look at maps from A to B tensor Q. And as well, in that case, I have universal co-measuring algebras. It's a bit more complicated in that case, but in our specific case of Frobenius algebra, we always know that this exists. And we can show that if I use Frobenius algebras again as my objects, and I consider my Hopf spaces to be these co-measuring algebras, I can show that this is an Hopf opcategory. So I didn't mention yet what a Hopf opcategory is, but it's a dual version of what a Hopf category is. So instead of having locally comonoid structure, but a global multiplication, the way of connecting my arrows, I want to look at local multiplication structure and global co-multiplication. So here now, for two objects, I always have little monoids with multiplication mx, xy, and units jxy, and I have algebra maps from some Hopf space from x to z, and I can split up an arrow into parts in xy tensor hx z, and I just use the conditions I had for Hopf categories, but I have to make sure that I use the inverse the local and global structure. So instead of first co-multiplying locally, I multiply globally, and vice versa. So I don't want to put too much in. emphasis on that, but it's nice to see that if we expected this dual theorem to hold, and we can also show that the dual version holds for this. So here is the second theorem we proved. The category of Frobenius algebras and universal co-measuring algebras is a Hopf category. So we have now this quite abstract two theorems, but we still are we still don't really know what's going on. So there's a few questions that arise from these structural results concerning specific examples. So what I want to talk for the rest of the talk is how to generate examples, how we generated examples, and how far we got. So luckily there's an efficient way of generating examples is here denoted by, I can just choose two Frobenius algebras. There's an explicit way of describing the co-measuring algebra by generators and relations. And there is a theorem that says I can dualize my co-measuring algebra, and this should be isomorphic to my measuring coalgebra. And since these, so if my co-measuring algebra is finite dimensional, the dualization process doesn't pose much difficulties, and I have a complete specific description of my measurings, and then I can figure out how does measuring actually work, how does it actually apply on specific elements of my Frobenius algebra. So there's a few questions we were posing ourselves before starting on working on these examples. In the case of Frobenius algebras and Frobenius algebra morphisms, since every morphism is invertible, we know that between non-isomorphic Frobenius algebras we don't have any errors. We don't have any morphisms between non-isomorphic algebras. So if we consider this wider class of maps, do we still have the same behavior? Do all these Hom spaces, these co-measuring spaces between different non-isomorphic Frobenius algebras, are they zero? And the other question we posed ourselves is like, are they always finite dimensional? So in this description of generators and relation, per se, we don't know if these are gonna be finite dimensional, or if they can blow up. And for some cases, we don't really have an upper bound on how big these can get. And generally, what structure do they have? Can we have a theorem that tells us for a specific example of a Frobenius algebra how are the co-measurings looking like? So I want to start with some non-examples, some propositions that you can show that answer a lot of these questions here negatively. So the first group of examples I looked at were group algebras, and you can show for group algebras that if you can, the first thing that is quite obvious is you can show that they are symmetric. So if I look at measurings from a group algebra to another, it's the same than looking at group algebras in the other direction, and the same holds for co-measurings and for measurings. So we already cut all our cases in half, and if I drew a diagram of all my group algebras, I know that it's going to be symmetric. But the first kind of bummer to our expectation was that if I have two groups, then the co-measuring algebra between these are only non-zero if they have the same size. So this is already quite, it's a step in the right direction, because we at least know that they have to have the same size, but it's not yet obvious that they have to be already isomorphic. So a second wave of non-examples is matrix algebras. So for matrix algebras, some similar behavior is you can see that for looking at matrix algebras, they for sure only have non-zero co-measurings between them if they are the same. And if I mix these two, if I look at measurings from matrices to group algebras, then I can see that there are no interactions between them whatsoever, except the trivial case where the dimension and the group is 0, so we're just considering the trivial Frobenius algebra structure. So these are a lot of conditions on what shouldn't work, but I was able to calculate at least 3 examples, and they're in this diagram. So if I look at group algebras and I look at the co-measuring algebras from one cyclic group to another cyclic group, then in size 1, this is just the base field. In size 2, we can show that it's isomorphic to the group algebra itself. And the first example that is exciting is if I look at the cyclic group of 3 elements, I can show that it's a direct product of 2 copies. But then afterwards, for groups of size bigger than 4, the calculations get really lengthy and tedious. So for bigger groups, the equations you have to consider by hand get bigger and bigger. So I think already in size 4 you have to consider a few, like 80 equations, and by hand this gets this is not really possible. So for example, the first little conjecture, or the first question we have is there a measuring from C4 to C2 times C2? We don't know that yet. You have a clear structure of how to do it, but you need to go through the construction of the algebra and see if you can interpret the structure. So to close my presentation, I want to also give some outlook on how this research could go on. So another way of saying is there a co-measuring between non-isomorphic Frobenius algebras is saying, is this category, this non-classical category constructed, is it just a collection of Hopf algebras, or is there actual material between these non-isomorphic Frobenius algebras? And we can carry on with these algebraic questions I mentioned. But to go back to my TQFT examples where I started, how do I fill in this diagram here? Is there a way of using that fact that I can have the fact that there's a Hopf algebra structure on the endomorphisms between Frobenius algebras? Can I use that to construct a 3-dimensional TQFT? And something that is still on the way. So we don't know if these are quasi-triangular, if these satisfy the extra conditions necessary to define 3-dimensional TQFTs. And the way of another question is there an analog of this work by Lauda and Pfeiffer of considering open and closed cobordisms in 3 dimensions to make sure that this observation actually has a geometric foundation? So to maybe give an idea of how the research is going, we start with something specific and some motivation. And we found this algebraic result, but now it's quite hard to get back into the context of TQFT. But on the way there's a lot of new interesting questions arising. And I hope I could give you a little insight of what we're doing. And I'm looking forward to your question if there are any. Thank you.